Hello, everyone. So today we're going to finish up all the theory classes. This is the last theory class for the semester. And after this, we're going to go to inferences. So the title is Distribution of Sample Mean, Central Limit Theorem. So this is the last theory class, right? So we're going to be done by today for this part. Please get familiar with all the symbols again. So all the symbols, just one page full. Small n, sample size. Big N, population size. Sigma, population standard deviation. S, sample standard deviation. Mu, population mean. X bar, sample mean. Z, standard normal variable. R, correlation. B1, regression slope. B0, regression intercept. P-value and alpha, we're gonna, talk about them very, very quickly when we talk about the inferences, all right? We're gonna go to inferences right after this. Learning objective, understand the relationship between sample and the population. We really went over this in chapter 8. So anytime you conduct the research, you're always gonna have a population and sample, right? Your research interest is the population, but your data collected will be from the sample, right? And then understand the relationship between statistic and the parameter. So we also talk about this in chapter 8, right? All the parameters are numbers describing the population, and the statistics are numbers describing the sample, right? So population parameter and sample statistic. And then understand what the central limit theorem is. And it provides a distribution of what statistic. So we're going to talk about it. And then very importantly, if you understand what the central limit theorem is, we need to use it to solve some practical problems. Okay. So we start with parameter and the statistic. You know, that's one is for population, one is for the sample, right? And then we have two distribution now. Two other terms associated with this. We have population distribution, we have sampling distribution. So the key word is basically, I want you to understand what's a sampling distribution, because the title is sampling distribution of sample mean, right? So population distribution is a distribution of the variable among all the individuals in the population. So that's the general population distribution we talked about. If you have a population, then how likely are all the individuals distribute, across all the sample space, right? So that's the general sense of distribution. What's the sampling distribution? Sampling distribution is a distribution from the sampling process. So it's talking about a distribution of a sample statistic in all possible samples of the same sample size if you were to do a random sample. Okay, so let's spend some time on that. So you have a population. Population has many, many individuals in there, right? So population, how the individuals distribute, that's population distribution. I'm all for writing like this. Maybe I use the typing. So you have population distribution based on the population you have, right? All right. So then when you conduct the research, you're not going to measure from the population, but instead, you're going to draw a sample. So this is your sample. And the process, you draw the sample, is going to be a random process. So then when you randomly select the sample, how many different possible samples can you have if you have a fixed sample size n? You're going to have many, right? So you could have many, many different samples if you randomly select, right? With the same sample size. Then in chapter 10, we talked about random variable. Random variable is a variable defined from a random process. And all random variable will have a distribution, right? So then if this is a random process. When you have different possible sample, then every sample is randomly generated, right? All the individuals are randomly selected. So if you can define a numerical variable out of this random process, then that numerical variable could have a distribution. So for example, you can define a numerical variable as x bar. For every possible sample, you're going to calculate x bar, right? The next bar will vary for every different sample you draw, right? So x bar is a random variable. Then we're going to have a distribution of x bar. And likewise, if you calculate standard deviation for each random sample, then you're going to have a distribution of sample standard deviation S, right? And if you calculate correlation from the sample, you're going to have a distribution of correlation, right? So every statistic from the sample is going to have a distribution, just depending on, when you randomly choose the sample individuals. And the distribution of the statistic, any of the statistic, is called sampling distribution. Okay, so that's sampling distribution, the distribution of any sample statistic of the same sample size. Okay, and in our class, we're only going to talk about the distribution of sample mean x bar. So we're only going to focus on distribution of x bar. Right? So we're not going to focus on other statistic. Maybe if you are going to take some advanced stats classes, you're going to talk about distribution of other statistic. But sample mean distribution is the easiest, and that's also the most important, right? Okay, so we're going to move on. So then, if you're still confused, let's still give another example about how do we find a sampling distribution, all right? So we're going to use a small population as an example. We have a population, I only have 5 numbers, 1, 2, 3, 4, 5, right? You only have 5 individuals, and the numbers are easy, okay? So we're going to start with that. Then what will be the population distribution? So we're going to draw a population distribution of it. So we have a population with values 1, 2, 3, 4, and 5. Now we want to draw this population distribution. So we can, even though population distribution, we use density curve to describe it, but a lot of times histogram and the density curve, they're very, very comparable. From histogram, we can describe the distribution of any populations, right? So let's try to make a histogram of this population. And we know to make a histogram, we need to make a frequency table, right? So we need to have a class defined, as well as we need to have a frequency counted, right? Frequency table. And in this class, I'm going to define first class as all the number between 0 and 1. And the second class is all the number between 0 and 2. between 1 and 2, and so on. But if you notice, I have different signs on, each of the class. It's on the left is parentheses, on the right is brackets, right? So what does it mean? If you take some math class, they may have indicated to you that anytime when you have parentheses and brackets on different side of the event, it just means all the values of x that's greater than zero, but at the same time smaller than or equal to 1, right? So basically it's right inclusive. The bracket side is inclusive. The parenthesis side is exclusive, right? So we make it this way just so that we don't have any overlaps on the classes, and that's required to, for frequency for the class, right? So then when you look at the population, you have 1 in first class, you have 1 in second class, you have 1 in third class, and 1 in fourth class, and 1 in fifth class, right? So that's an easy frequency table. Then based on this frequency table, we can draw histogram, right? So this is your variable x, and this is frequency, right? So then we label the axes 0, 1, 2, 3, 4, and 5, right? And then here you label 0, 1, and 2. Okay, so then we need to draw bars, 1 bar for each class, right? With corresponding height as the frequency. So for 0, 1 class, we're going to draw a bar right here for between 1 and 2, a bar here, 2 and 3, here, 3 and 4, here, and it's 4 and 5 here. So this is distribution of the population, right? So this is a population distribution. So it's a distribution of the population, right? So now what's the sampling distribution? So sampling distribution, we need to determine sample size first. So what sample size do you want? We're going to choose a small sample size for n equal to 2, okay? So if you choose sample size equal to 2 from the population 1, 2, 3, 4, 5, so what possible samples can we get? Right? So you choose 2 individuals randomly from the population, right? So you could get 1 and 2, right? And you could get 1 and 3. You could get 1 and 4, right? Then what other samples could be there? 1 and 5. And then 2 and 3. 2 and 1 is the same as 1 and 2, right? They're the same sample being chosen. Then 2 and 4. And 2 and 5. Then 3 and 4. And 3 and 5. And 4 and 5, right? So then for each of the sample, we are able to calculate the sample mean x bar, right? So if you have a sample with numbers 1 and 2, sample mean x bar will be what? 1.5, right? And if you have 1 and 3 as samples, sample mean will be 2. And 1 and 4, sample mean will be 2.5. 1 and 5, sample mean will be 3, just taking average, right? Sample mean is average of the sample. 2 and 3, average 2.5. 2 and 4, average is 3. 2 and 5, average is 3.5. 3 and 4, average is 3.5. 3 and 5, average is 4. 4 and 5, average is 4.5. So X bar could be any of these values, right? From this population. So X bar is going to change, but what kind of distribution does X bar have? To describe the distribution X bar, we can make a histogram of X bar, right? Just like we describe the distribution of X, we make a histogram of X, right? So then we're going to make a frequency table just like this, what we did here, okay? The class is going to be the same, but the frequency is going to change, right? We're going to use the same class. Then how many X bar do we have between 0 and 1? We don't have any, right? The smallest X bar is 1.5. And how many X bars between 1 and 2, including 2? So we have 1.5 and 2. We have 2 of them. How many X bar are there between 2 and 3? So we have 2.5, 3, 2.5, and 3. We have 4 of them. And between 3 and 4, we have 3.5, 3.5, and 4, including 4, right? So I have 3. And then between 4 and 5, only 1. So now, if you draw a histogram based on the frequency table here, so now this is X bar, right? So we're trying to describe the distribution of X bar. This is not X anymore. And this is frequency. So we learned histogram quite a while ago, right? This is chapter 1. Don't forget about it. You know, if you forget, just go back and review a little bit. And we're going to label just like how we labeled earlier. 0, 1, 2, 3, 4, 5. And then we're going to label here 0, 1, 2, 3, 4. So we're going to draw bars for class 0 to 1. The bar height is 0, right? The frequency is 0. It's a baseline. Between 1 and 2, we're going to draw a bar with height of 2. And between 2 and 3, we're going to draw a bar with height of 4. And between 3 and 4, we're going to draw a bar with height of 3. And between 4 and 5, we're going to draw a bar with height of 1. So then this is a histogram of X bar, right? And what kind of distribution is this? This is not a population distribution anymore. This is talking about distribution of a sample statistic, X bar, right? So this is a sampling distribution of sample mean X bar. You know, you can do sampling distribution of sample standard deviation, right? All you need to do is just calculate sample standard deviation instead of X bar, right? But we are only going to talk about distribution X bar. Okay, so then we know that for population distribution, the sampling distribution, they look different, right? But are there any kind of rules? Can we know what kind of distribution X bar will have? We have different population to start with. Will the sample mean X bar have a different distribution? Or maybe not, right? So we want to study this distribution. Then for any population, we can do the same process to study the distribution of sample mean X bar, right? Just doing exactly the same process, right? But when the population size is big, if you want to do the manual work like this, it's going to take forever, right? You don't want to do the manual work like this. So instead, we have computers that can help us to do the simulation. So, here we're going to show you some results from the simulation. So this is the first animal for attendance points. This is a hyena. Right. So in here, we're going to start with a few different populations. We learned normal distribution, right? We just finished it. We learned binomial distribution. And we learned uniform distribution. Not really in much detail, but remember in the density curve, we have a flat rectangular shape density curve. That's what a uniform distribution is. Okay. And then there's a Bernoulli distribution. You can treat Bernoulli distribution as a special binomial distribution, but n is fixed to be 1, right? And you can see all the formulas are very similar. Basically, if you set n equal to 1, the binomial is Bernoulli is the same, right? Okay. And the Poisson distribution. Poisson distribution is also a discrete distribution like a binomial, but the difference is binomial distribution has a fixed number of n, right? But the Poisson distribution doesn't. Okay, so the sample space will be from 0, 1, 2, 3 up to infinity, but it has to be a whole number. And binomial distribution have to stop at the cap, fixed number of n. But Poisson distribution, there's no cap. So then for each of the distribution, you can generate a population. Then we're going to do the same process as what we do here. And we're going to choose 4 population to work with. One is Z distribution, normal 0, 1. One is Poisson distribution with parameter 1. One is Bernoulli distribution with parameter 0.75. One is uniform distribution with parameters 0 and 12. So for each of the distributions, we can find a mean and standard deviation very quickly. So for example, Poisson distribution with parameter 1, then population mean equal to the parameter 1, right? Then for Bernoulli distribution with 0.75 as a parameter, population mean will equal to that parameter 0.75. And uniform distribution between A and B, and the population mean will be A plus B divided by 2 will be 0 plus 12 equal to 6, right? So keep that in mind. Then for each of the population, we're going to do the process. This is the simulation process. We're going to generate 100,000 random numbers from each of the distribution to serve as a population. So instead of 5 individuals as a population, as a small size population, now we're going to make a population that has 100,000 individuals, right? So that's pretty large population. And then we're going to take a random sample from the population. So we're going to choose sample size of 10 to start with. And then we're going to calculate the sample mean, right? And then we're going to save it. So just like when you have sample, we choose sample size of 2, and then we choose a sample, 1 and 2, we calculate the sample mean and save it, right? And we're going to continue to choose a different sample, and we save the sample mean. And then we do another sample, we do a sample mean, right? So it's the same process here. So we're going to repeat 5,000 times. Every time we're going to do a random sample with sample size of 10. So you have 5,000 different samples, right? And each sample will give you a sample mean. So you have 5,000 different sample means. Hopefully that number is good enough to evaluate the distribution of a sample mean, right? So we put that into a histogram to see what kind of distribution sample mean have. Just like here, we put all 10 sample means into a histogram, right? So over there, we just put 5,000 different sample means, right? If you think 5,000 sample mean is not good enough, you can make, 10,000, right? 20,000. The computer can do it very quickly. So then after we finish sample size of 10, then we can change sample size to be, different numbers. You have 25 individuals or 50 or 100, and you want to see if sample size will play a factor in the distribution of X bar. okay? All right, so then we're gonna look at the results. So we're gonna start with a normal distribution, 0, 1, Z distribution. So the center is 0, that's population mean, the standard deviation equal to 1, right? So this is a population distribution, right? This is symmetric bell-shaped curve. And then if we choose sample size of 10, 25, 50, and 100, keep in mind, these 4 distributions are sample distribution of X bar. They're distribution of X bar just like this, right? So then when you look at the distribution of X bar, when sample size of 10, what does it look like? We have symmetric bell-shaped distribution, right? That's a signature of a normal distribution, right? And once it look like a normal distribution, it always look like a normal distribution afterwards, right? So we can observe X bar has a normal distribution, right? So that's one thing we can observe. And the next thing we can observe is when you look at the distribution of X bar, where is the population mean of X bar located? You can see the center of X bar always pointing to 0, right? So population mean of X bar, if you recall, what's the population mean of X? Is 0, 1, right? Normal 0, 1. So population mean of X bar is the same as population mean of X. So maybe you can use a symbol instead of typing it. It's a lot easier. So if we use population mean as mu, so basically mu of X bar is the same as mu of X, right? And the next thing we can look at is, what about the standard deviation of X bar? At least when you compare the different sample sizes, when sample size change from 10 to 25 to 50 to 100, what happened to the standard deviation of X bar, the spread of X bar? The spread of X bar will decrease when sample size increase, right? So standard deviation of X bar will decrease when sample size increases. So that's what we observe if we start with a normal distribution. So what if we start with a different distribution? This is a Poisson distribution with parameter equal to 1. So that means population mean equal to 1 as well, right? So this is 0, 1, 2, 3, 4, 5, 6, 7, up to infinity. The probability decays exponentially, right? So this is a population distribution. Then if you draw samples, this is sample distribution of X bar when sample size is 10, and this is when sample size is 25, 50, and 100. Right? So we notice in the beginning, the distribution is not, doesn't have a normal look, right? What if the sample size is 50? What does it look like? Symmetric bell-shaped distribution, right? That's a signature of normal distribution, right? So then from here, we can observe that X bar has a normal distribution, but it has a condition now, not always. Only if sample size n is large, right? In this case, large is 50, right? Then X bar will start have a normal distribution. Then what about the population mean of X bar? You can see the center always pointing to 1, right? And that's original population mean as well, right? So population mean of X bar is the same as population mean of X. And if you look at the population standard deviation of X bar, so when sample size increases from 10 to 25 to 50 to 100, we can see the spread of X bar will decrease, right? So that's the same information as we observed from the other distribution. So what if we start with a different distribution now? We use a Bernoulli distribution. Bernoulli distribution, the variable X can only take two possible outcomes, 0 and 1. Right? So probability being 1 is success is 0.75. Probability being 0 is 0.25, right? So this is the population distribution. You basically have a bunch of zeros, you have a bunch of ones, right? And then if you take a random sample with sample size of 10, this will be the distribution of X bar. This is 25, distribution of X bar. This is 50, distribution of X bar, and 100, distribution of X bar, right? So maybe when sample size is 50, it still doesn't look like normal, but when sample size is 100, you can see this is very, very good looking of bell-shaped symmetric normal distribution, right? So then when you look at this simulation, when sample size n is large, this time large is 100, right? So X bar will start to look at normal distribution. What about population mean of X bar? You can see the center is pointing at 0.75, right? Which is the same as the original distribution, population mean, right? So population mean of X bar will be the same as population mean of X. And then population standard deviation of X bar, when you look at the trend, when n increases, the spread will decrease, right? So population standard deviation of X bar will decrease when n increases, okay? So we can see that we observe exactly the same feature when you start with different distributions, right? So we're gonna look at the last distribution. This is a uniform distribution, right? So uniform distribution, basically every number has the same chance to occur between 0 and 12. This is a population distribution. Now let's look at the sampling distribution. This is sample size of 10, 25, 50, and 100. And surprisingly, when sample size of 10, the X bar already have a very good normal look, right? Symmetric bell-shaped. Then once it start to look like normal, then when you increase sample size, you're gonna stay that normal look. So X bar have normal distribution at n is greater than 10, right? And then population mean of X bar, you can see this is 6, right? Original distribution is between 0 and 12, then population mean is 6 as well. So population mean of X bar is the same as population mean of X. And then population standard deviation of X bar, you can see standard deviation of X bar will decrease when n increases, right? So basically here we can conclude for any population, it looks like it doesn't matter what population you start with, you're gonna have the same conclusions here. If n is large, then the sample mean will have a normal distribution. With population mean, the same as original population mean, and the population standard deviation has a decreasing trend when you increase the sample size. And basically that's what central limit theorem says. So basically central limit theorem says if sample size n is large enough, sample mean will always follow a normal distribution. And the normal distribution has two parameters, mu and sigma, right? Mu of X bar will be the same as mu of X. And the standard deviation of X bar will be standard deviation of X divided by square root of n. You can notice that the feature of when n increases, standard deviation of X bar will decrease, right? So we always say that normal distribution is the most important distribution in statistics. Why is that? Is it because we have a lot of variables have normal distribution? No, we don't have many variables in life that's normal distribution. The reason normal distribution is most important is because of the central limit theorem. So basically, doesn't matter what kind of population distribution you have, doesn't matter what kind of data you have. As long as you take a sample, a random sample, with a large enough sample size, your sample mean will always have a normal distribution. So with that, you can use normal distribution to analyze any kind of data, as long as you make sure sample size is large. So that will make a normal distribution a universal tool for any kind of data analysis, as long as your sample size is large enough, right? So that's what makes normal distribution so special. All right, so this is central limit theorem, and it's basically for the whole class. We're just learning this one sentence. And once you know that, the rest is just normal process we just finished in chapter 3. Right? So don't forget about normal distribution. We're going to use it quite a lot. Okay. So this is the second animal for attendance point. This is a sea turtle. All right. So we're going to look at practice questions. We're going to practice on these. Almost all medical schools in US require students to take medical college admission test, MCAT. And the MCAT score follows a normal distribution with mu equal to 25 and sigma equal to 10 for a college. If you chose one student at random from the college, what's the chance the student scores between 20 and 30? This is actually a typical normal distribution problem. There's nothing new in this question, so you didn't use central limit theorem yet. So when you look at a problem, if you define variable x as MCAT score, then we know the variable x will have a normal distribution with mu equal to 25 and the standard deviation sigma equal to 10, right? And what we're looking for a probability. Probability of x is between 20 and 30, right? So this is a typical normal distribution problem. You have a normal distribution with parameter provided. You're looking for normal event probability, right? So from what you learned in chapter 3, we're going to standardize this. So we're going to trying to build an equation. All right. So on the left-hand side, we're going to use 20 minus mu. Mu is 25 divided by sigma. Sigma is 10, right? And in the middle, we're going to do the same thing, except that it's not 20 anymore. It's going to be x, right? And then on the right-hand side, same thing, except that the boundary is 30 now, right? So z equal to x minus mu divided by sigma. Then it will become probability of a z event, right? So in the middle becomes z, and on each side we can calculate the number. 20 minus 25 is negative 5 divided by 10, negative 0.5. In the middle becomes z, on the right-hand side is positive 0.5, right? So then this is a z event. We can look up the probability. Will be probability of z less than positive 0.5 minus probability of z less than negative 0.5, right? If you're confused about this, you can watch the chapter 3, part 1 video. There's, we explain why we change this way using the density curves. Okay. And then we can look up in the Z table, right? So with both event, we have less than sign. So we're good to use Z table as is. So if you look up positive 0.50, probability is 0.6915. So this will be 0.6915 minus, then you look for probability of Z less than negative 0.5. So we look for negative 0.5 is here, 0.50, right? So it's 0.3085. And then we do the math, right? So 0.383. So that's part one. There's nothing new. This is just a typical normal distribution. So now B, if you get a simple random sample of 25 students, what is the sampling distribution of average score of the 25 students, basically, right? So 25 students is a sample. We're looking for a distribution of sample average, sample mean, right? So we're looking for a distribution of X bar. The only one place will give you a distribution of X bar, that's from central limit theorem. And from central limit theorem, X bar will follow a normal distribution with parameters mu and sigma over square root of the band. Okay, so I'm going to copy that over here so that I don't have to type it. And now we need to figure out what each of the parameters are, right? What is mu of X? Mu of X will be 25, right? And what's sigma of X? That will equal to 10, right? It's from here. This is mu of X. This is sigma of X, right? Then what is N? N is sample size. Sample size is 25 students, right? We have 25 students as a sample. So then a little calculation here. We know X bar will have a normal distribution. And the parameter will be 10 divided by 5, which is 2. Okay. So sometimes you can use the subscript n, or you can just leave it out there. You don't have to indicate the sample size. And part 3, what's the probability that the average score of the 25 students is between 20 and 30? Okay, so now you need to make sure you note the difference between part 1 and part 3. So we're looking for probability of X bar is between 20 and 30, right? It's not X anymore. It's average of the sample is X bar, right? Okay. So when you write the events out, please have a good distinction between X and X bar. They're different variables and they have different distributions. Okay. So X bar has a distribution of normal with 25 and 10 as a parameter. X bar has normal distribution with 25 and 2 as a parameter, right? So X and X bar has totally different distribution. If you're dealing with X, use distribution of X. If you're dealing with X bar, use distribution of X bar, right? Okay. So now we're gonna work on this. Since X bar is normal distribution, then we're gonna just use normal process, right? So we're gonna copy the formula I used there, but I need to change the things in there, okay? So in the middle will be X bar minus 25 instead of just X, right? And on the left is 20 minus mu, 25. That's good. But sigma of x bar equal to what? Sigma of x bar equal to 2, not 10, right? So sigma will be equal to 2 for x bar. And then the rest is the same. So this will be standardized into a z event. On the left is negative 2.5. And then the middle will become z, right? And on the right-hand side is positive 2.5. So then we convert it to be probability of z less than 2.5 minus probability of z less than negative 2.5. And then we look up the z table. They're both smaller in size. We can look up the z table as is. So positive 2.5, 0. The corresponding probability is 0.9938. So 0.9938. And the negative 0.5, we can look up in the z table as well. So negative 2.5, 0. Corresponding probability is 0.0062. And then we do the math, right? So 0.9876. And then the problem is solved, right? So please note the difference between question C and question A. They're asking for this distribution of different variables. This is for original population X. This is for sample mean X bar, right? Okay. The next question, the weight of the fish in a lake has a normal distribution with a mean of 4 pounds and a standard deviation 2.1 pounds. If a guy Sam went fishing one day, he caught 6 fish. If we suppose the 6 fish he caught is a random sample from all the fish in the lake, what is the chance that the average weight of the 6 fish he caught is greater than 5 pounds? Right? So the key thing is, again, you're looking for probability related to average weight of a sample, right? So you're looking for probability of X bar. And probability X bar is greater than 5. This is what they're looking for, right? So if you want to find probability related to X bar, you need to find the distribution of X bar. And the only place to give you the distribution of X bar is from central limit theorem. So X bar will have a normal distribution with mu of X and a sigma of X over square root of n. Mu of X is 4, sigma of X is 2.1, and n is 6, right? That's a sample size. You have 6 fish as a sample. So then if you do a little calculation, X bar is normal with population mean is 4 and the population standard deviation is 0.86. So 2.1 divided by square root of 6 is 0.86. Then for probability of a normal event, X bar greater than 5, you need to standardize X bar using the distribution of X bar, right? And then it becomes a Z event. Watch out for the sign, greater than sign, subtract from 1, right? And you look up in the Z table, you have 12.3%. Okay. And now another example. Averagely, a kid would drink 2 gallons of water every day with a standard deviation 0.7 gallon. A school is organizing for a whole day camp with 100 kids, and they're bringing 210 gallons of water. What's the chance that water will run out? Okay. Some people got confused with a question like this. So we're gonna do it slow here. We're looking for probability of water runs out. So now we just need to explain this. What does it mean when we say water runs out? Then go back to the scenario. So water runs out. How much water do you bring? 210 gallons of water, right? and you bring 200, you're bringing 100 kids with you. So when will water run out? When water runs out, what does it indicate? So it indicates the total water consumed by those 100 kids is greater than 410 gallons, right? So here is total. If this is average, then it's really X bar, right? But this is total, not average. From total to average, what do we need to do? If we divide both sides by sample size, 100. So the probability will stay the same, right? Basically, divide both sides by a number, then the probability will stay the same. But then now when you look at it, total water consumed by 100 kids divided by 100 kids, that will become what? That will be average water consumed by those 100 kids, right? And that will be greater than 2.1 gallon, right? So now this is average. So average water by the sample, right? Sample average. So now it becomes sample mean X bar. Greater than 2.1. All right. So once you converted the event probability into an event related to X bar, the rest is exactly the same process. So then we need to find the distribution of X bar from central limit theorem. From central limit theorem, X bar will follow a normal distribution with parameters mu of X and sigma of X over square root of N, right? Then we just need to plug in numbers, right? X bar will follow a normal distribution. What is mu of X? Mu of X will be average water consumed by a kid will be 2 gallon, right? That's given. And the sigma of X is standard deviation of all the kids, right? So that's 0.7. And divided by square root of N. What is N? The 100 sample is the 100 kids is the sample. The sample size is 100, right? So then with a little calculation, we can say that X bar has a normal distribution with population mean is 2 and the population standard deviation is 0.07. So this is the distribution you need to use to standardize this event, right? So if I put this on top, we can continue to work on this. So this will be probability of on each side. We're going to standardize, right, by using z equal to x minus mu divided by sigma, right? So we're going to use x bar, subtract the mu. Mu is 2 divided by sigma, 0.07, right? So the parameters are right here. Then keep the sign as is. On the other side, we're going to do the same operation, except that this is not x bar anymore. This will be 2.1. So then we standardize. This will be probability of z greater than, and we calculate, right? So 2.1 divided by 2.1 minus 2 is 0.1 divided by 0.07. That'll be 1.43. So then this is a z event. We should be able to find its probability using z table, but watch out for the sign, right? So we need to convert it to be smaller than sign before we go to z table. So then we look it up. 1.43, if you go on the z table, 1.43. So the probability correspondingly is 0.9236. Right, so 1 minus 0.9236. And do a little calculation, 0.0764. So converted to percentage, 7.64%. So that's the answer, right? So about 7.64% of the chance that the water will run out. So, you know, this is a good example that central limit theorem can be applied in some planning, right? So if you're planning this camp and you find out that the chance of water right now is too high, then you just need to bring some more water, right? Then if you think the chance is not too high, you know, it's good, then you can just go ahead and carry it out. So central limit theorem is the reason that normal distribution is so important. So it doesn't really matter what kind of distribution your population has. So for example, in here, the kids' water consumption amount, what kind of distribution does it have? We don't even know. It didn't tell us, right? But as long as you can apply the central limit theorem, you know, the sample mean x bar will start to have a normal distribution. So you can use normal distribution to analyze any kind of problem. That's the beauty of the central limit theorem. And that's the reason why normal distribution is so critical and so powerful. Right? So this will be the end of the theory part. And after this, we're going to go back to application for making inferences. And the central limit theorem is the foundation of all the inferences we're going to talk about in this class. So please have a good understanding of the central limit theorem as well as the normal distribution. That will help you a lot for, you know, the following concepts. Right? So thank you very much. Let me know if you have any questions. Right? Thank you.